In this lesson, we'll start by checking that we can use the basic point of safe return equation. Here is a typical question. Your total endurance is 7 hours and 40 minutes. Required reserves are 1 hour and 40 minutes. The true airspeed is 200 knots. The distance from departure to destination is 1200 nautical miles. The outbound wind component is 30 knots tail. Assume that the wind remains constant. What is the time and distance to the point of safe return? These are the possible answers. Don't click onto the next scene until you have the answers. Let's go through it. Your total endurance is 7 hours and 40 minutes. However, the required reserves are 1 hour and 40 minutes. These must be available on arrival back at the departure airfield. This leaves 6 hours safe endurance. The true airspeed is 200 knots. The distance from departure to destination is 1200 nautical miles. But this is irrelevant to the question. It will make no difference to the point of safe return. The outbound wind component is 30 knots tail. So O will be 200 knots TAS plus 30 knots. This gives a ground speed of 230 knots. We can assume a constant wind. So the wind component on the return part of the flight will be 30 knots head. Therefore H will be 200 knots TAS minus 30 knots. This gives a ground speed of 170 knots. Write down the standard equation T equals EH over O plus H. Substitute your known values for E, O and H, and you should have got 2.55 hours, which is 2 hours and 33 minutes, or 153 minutes. The distance to the point of safe return is O times T. O is 230 knots, and T is 2.55 hours, which comes to 586.5 nautical miles. We'll call that 587 for all practical purposes. So answer A was the right one. These basic equation questions are fairly straightforward. There are only 2 points to watch out for. One is, don't use the point of equal time formula for a point of safe return question, but we have covered that. The other is if you are given a wind velocity instead of a wind component. The geometry of the triangle of velocities does not always give a tailwind component of the same value as the headwind reversed. You have to solve the triangles with a navigation computer in both directions. If you make approximations of the wind component using rule of thumb methods, or assume that the tailwind component is the headwind component reversed, you may well get the wrong answer. All the solutions that we have seen up till now make the assumption that the fuel is used at a constant rate and that endurance is linearly related to fuel contents. This may be unrealistic. This would assume that a fuel graph, or how goes it as it is often called, takes this form, with a straight line graph of fuel against time or distance. In fact, a practical how goes it usually looks more like this. There is an initial steep slope, because the climb is usually carried out at maximum continuous power, whilst once at top of climb, it is normal to set long-range cruise. So the fuel flow rate is higher. In addition, the aircraft is usually climbed at a slower speed than in the cruise, so the distance covered in the time is less. Once at top of climb, the aircraft is heavier than it will be later in the flight when some fuel has been burnt. The fuel flow per nautical mile will therefore be greater. If the aircraft is flown using a constant power setting, the speed will be slower in the early part of the flight, whilst if the aircraft is flown at a constant speed, more power and therefore more fuel will be needed whilst the aircraft is heavy. However, as the weight reduces, the kilograms per nautical mile will increase, and the slope will reduce. There is another reason why the fuel flow may not be constant. Point of safe return procedures are not an emergency, and they will therefore be flown at the correct semicircular flight level to conform to air traffic control regulations. Even if all other factors were equal, we would expect the true airspeed and fuel flows to be different on the outbound and return legs. To cope with this usually more realistic situation, we have another equation. Rather than derive it by algebra, we shall simply quote it. We will then do a worked example, and the way that it works will become obvious. D is the distance to the point of safe return. F is the safe fuel. This is quoted in kilograms or pounds or gallons, or whatever units are used for that aircraft, not in time. As it is the safe fuel, it does not include the reserves. If the reserves were included, it would be called total fuel. CO is the specific ground range outbound. Specific ground range is fuel used per nautical ground mile. CH is the specific ground range homebound. The formula to be used is D equals F over CO plus CH. Now let's see how it is used. Here's the formula again. We'll say that we fly outbound to the point of safe return at flight level 270 and return at flight level 310. F, our safe fuel, is 39,500 kilograms. Our TAS remains constant at 310 knots. We have 30 knots tailwind outbound and 30 knots headwind inbound. The fuel flow outbound at flight level 270 is 6,250 kilograms per hour, and the fuel flow homebound at flight level 310 is 5,300 kilograms per hour. We need to find CO and CH. The first thing to do is calculate O and H. O is 310 knots TAS plus 30 knots tailwind. That's a ground speed of 340 knots. H is 310 knots TAS minus 30 knots headwind, or 280 knots ground speed. CO is fuel flow outbound divided by ground speed outbound. Let's see why. We use 6,250 kilograms per hour outbound, and our ground speed outbound is 340 knots. However, another way of describing ground speed in knots is that it is nautical ground miles per hour. We are dividing by per hour in both the numerator and the denominator, which means that they cancel. The answer is 18.382 kilograms per nautical ground mile. We apply a similar logic to CH. It is 5,300 kilograms per hour homeward, divided by 280 knots ground speed home. Again, the per hours cancel, this time giving us 18.929 kilograms per nautical ground mile. So, CO plus CH, the bottom line of our equation, comes to 18.382 plus 18.929 kilograms per nautical ground mile, which totals 37.31 kilograms per nautical ground mile in both directions. Let's draw in 1 nautical ground mile. Here it is. We use 18.382 kilograms flying out and another 18.929 kilograms flying back, making a total of 37.31 kilograms there and back. So all we have to do is see how many times we can fit 37.31 kilograms into 39,500 kilograms, which is all of our safe fuel. It comes to just over 1,058 nautical miles. So now that we have the distance, we can find the time from the ground speed outbound. The time will be this distance divided by O, which is 340 knots. Let's summarize this lesson. We revised the basic point of safe return equation, the one you should normally use if the fuel flow can be assumed to be constant. It was T equals EH over O plus H. We also reminded ourselves not to use the point of equal time formula for a point of safe return question, and of the need to use the navigation computer to properly solve the triangle of velocities in both directions if given a wind velocity instead of a component. However, we then found that the basic formula is based on the assumptions that the fuel is used at a constant rate, and that endurance is linearly related to fuel contents. This may be unrealistic, firstly because the fuel consumption changes as the weight reduces, and secondly because the outbound and return legs may be flown at different flight levels. To cover the case of variable fuel flows, we have another equation. D equals F over CO plus CH. And we saw why this works by showing a worked example.